Welcome to the Shika Serbu Motor channel. This channel provides easy-to-understand explanations of car mechanisms. The topic of this video is CVTs. The contents are the structure and function, the advantages and disadvantages, the varieties of CVTs, the history, and the future of CVTs. The structure of a CVT is typically simple, where the engine rotates input to the primary pulley and it transmits to the secondary pulley through a belt. This rotation outputs from the secondary pulley to the wheels. Some CVT models use a chain instead of a belt. Reducing the primary pulley width causes an increase in the effective diameter of the primary pulley, and a decrease in the effective diameter of the secondary pulley. This results in a lower reduction ratio, leading to higher rotational speed of the secondary pulley. Conversely, increasing the primary pulley width results in a higher reduction ratio, causing a decrease in the rotational speed of the secondary pulley. In other words, a CVT is capable of continuously altering the vehicle's speed, while keeping the engine rotational speed constant. In a typical pulley system, frictional force operates between the rope and the outer circumference of the pulley. Therefore, the rope conveys force in the direction of being pulled. In a CVT, frictional force is generated between the cone surface of the pulleys and the side surfaces of the belt. The belt conveys force in the direction it's pushed. To generate this frictional force, a CVT creates high hydraulic pressure to push the pulleys and clamp the belt between the cone surface of the pulleys. Furthermore, hydraulic pressure is necessary to control the primary pulley width for changing the ratio, and thus a CVT has two separate hydraulic circuits. The hydraulic pressure for clamping the belt is referred to as the line pressure, and the hydraulic pressure for changing the pulley width is referred to as the pulley ratio control pressure. To increase speed, the pulley ratio control pressure is increased, pushing the primary pulley to narrow the pulley width. As the belt is pulled towards the primary pulley side, the width of the secondary pulley is expanded by the belt. To reduce speed, the pulley ratio control pressure is reduced. Because the line pressure narrows the secondary pulley width, the belt is pulled towards the secondary pulley side and the width of the primary pulley is expanded by the belt. Today, a torque converter is used for launch and stop control. In the past, there were vehicle models that utilized electromagnetic clutches or hydraulic multiplate clutches for this. The torque converter transmits power through two facing impeller blades, within an oil-filled torque converter case. It can be used as a launch device in CVTs and step-type automatic transmissions, because it allows the output side impeller to be stopped while the engine is still running. If you want to learn more about torque converters, please watch the video, How an Automatic Transmission Works. The link is provided in the description. Forward and reverse control is achieved through a double-pinion planetary gear set. The double-pinion planetary gear employs meshed two-pinions gear sets. When the planetary carrier and sun gear are connected, all elements rotate as one unit. The input rotation speed into the sun gear output from the planetary carrier with same rotation speed. When the brake applies the internal gear to hold it in place, the input rotation speed into the sun gear is reversed and reduced, and then output from the planetary carrier. During forward motion, the planetary gear set is rotated as a unit. While during reverse motion, the internal gear is fixed to cause the output shaft to rotate in the opposite direction. Depending on the transmission model, the planetary gear is placed on the input side. The advantages of CVTs include smooth acceleration without shift shocks, changing vehicle speed whilst maintaining the most efficient engine speed, and a simple structure with fewer components. Let's take a closer look at changing vehicle speed with maintaining at the most efficient engine speed. These graphs represent the performance curve of a certain engine. Compare the acceleration characteristics between the CVT and the step-type AT with this engine. In a step-type AT, the engine speed changes with each shift changing, whereas in a CVT, it can accelerate while maintaining the engine speed with the lowest fuel consumption rate. This is the reason that CVTs are said to be more fuel efficient under certain conditions. The disadvantages of CVTs include lower efficiency compared to manual transmissions and step-type ATs, narrower range of gear ratios compared to step-type ATs, and a unique acceleration sense that differs significantly from other transmission types. There are several reasons for the lower efficiency. Gears typically used in manual transmissions or step-type ATs have a transmission efficiency of around 99%, whereas in the case of CVTs with belts and pulleys, even under the most efficient gear ratios, the efficiency remains above 90%. Furthermore, the hydraulic pressure required to generate friction between the belt and pulleys is typically around 5 megapascals, which is significantly higher than the approximately 2 megapascals required to actuate the clutch in a step-type AT. As a result, the losses incurred by the oil pump contribute to reduced fuel efficiency. In the latest CVTs, they control the oil pump function to generate higher line pressure during only heavy load conditions, such as high-speed driving or rapid acceleration to improve fuel efficiency. In step-type ATs, the range of gear ratios can be significantly increased by adding more gear steps, whereas in CVTs, there is a limitation in increasing the pulley diameter, preventing the expansion of this range to a large extent. Honda's latest 10-speed AT has a gear ratio range of 10.1, Fiat and Chrysler's latest 9-speed AT offers a gear ratio range of 9.819. In contrast, Subaru's latest CVT has a gear ratio range of 8.098. The difference in acceleration sense is brought by controlling the engine speed to maintain a constant. In manual transmissions or step-type ATs, the vehicle speed increases synchronize with the rise in engine sound. In CVT, only the vehicle speed increases while the engine speed remains constant. This gives the driver a sense of discomfort. Attempting to improve this, one of the major advantages of CVTs would be lost. Some sports models with CVT equipped with a pseudo-manual transmission mode. The driver can operate the paddle shifters on the back of the steering wheel to shift up and down, simulating a manual transmission. The Subaru WRX CVT model has an 8-speed simulated steps. The Toyota GR Yaris CVT model features a 10-speed simulated steps. Conventional CVTs typically use belts for power transmission, but Subaru employs chains. Chains can be bent around smaller diameters than belts, allowing for a wider range of gear ratio and superior power transmission efficiency. However, the drawbacks include increased noise levels and higher costs. Some CVTs are equipped with a secondary gearbox. Incorporating a 2-speed planetary gear type shifting mechanism on the secondary pulley output shaft aims to expand the range of gear ratio and achieve a compact transmission through the reduction of pulleys diameters. The drawbacks include a complex mechanism, increased weight, and higher costs. The D-CVT from the Japanese manufacturer Daihatsu features a highly innovative structure. To understand D-CVT, it is necessary to first comprehend the mechanism of planetary gears. If you are familiar with planetary gears, please use the seek bar to skip this chapter. A planetary gear consists of 3 components: an internal gear, a sun gear, and a planetary carrier. The internal gear has teeth on its inner circumference located on the outer side. The sun gear is at center. The pinions connect the sun gear and the internal gear, and the planetary carrier assembles the pinions. The pinions rotate individually and also rotate together with the planetary carrier. Let's try applying the brake to the internal gear to prevent it from rotating, and applying an electric motor to the sun gear shaft for input rotation. The input rotation speed into the sun gear is reduced, and then output from the planetary carrier. When the electric motor is applied to the planetary carrier, the input rotation speed into the planetary carrier is increased, and then output from the sun gear. Next, let's apply the brake to the sun gear to hold it in place. The input rotation speed into the planetary carrier is increased, and then output from the internal gear. The input rotation speed into the internal gear is reduced, and then output from the planetary carrier. Lastly, let's apply the brake to the planetary carrier to hold it in place. The input rotation speed into the internal gear is reversed and increased, and then output from the sun gear. The input rotation speed into the sun gear is reversed and reduced, and then output from the internal gear. Let's try thinking of this planetary gear as a transmission. Attach the tires to the internal gear, and install an electric motor on the planetary carrier in place of the engine. Due to the friction between the road surface and the tires face significant resistance, so when the planetary carrier is rotated with the electric motor, the sun gear will rotate idly. When a braking force that is greater than the resistance on the tire is applied to the sun gear to hold it in place, the internal gear and tire rotates, allowing the car to start. When the braking force is slightly reduced, the sun gear rotates slowly, and the rotation speed of the internal gear is reduced. Further reducing the braking force causes the sun gear rotation speed to increase, while the internal gear rotation speed is reduced even further. First, let's take a look at the structure of the DCVT. This is a conventional CVT. However, the input shaft rotation is reversed and input into the primary pulley. The input shaft gear is mounted on the input shaft through a hydraulic multiplate clutch. The planetary carrier of the output side planetary gear meshes with the input shaft gear. The sun gear is fixed to the output shaft of secondary pulley. The internal gear outputs the rotation to the differential side. At low vehicle speed rang, the planetary gear rotates as one unit by connecting the two elements of the planetary gear. In other words, the DCVT operates as a belt-type CVT. At high vehicle speed range, it still operates as a belt-type CVT. When certain conditions are met, the hydraulic multiplate clutch on the input shaft engages the input shaft and the input shaft gear, and each element of the planetary gear releases to free. The rotation to drive the tires is input from the input shaft gear to the planetary carrier, and output from the internal gear. The rotation transmitted through the pulley and belt rotates the sun gear. As explained of the operation of the planetary gear in previous chapter, varying the sun gear rotation speed changes the gear ratio of the planetary gear. In summary, the DCVT operates as a belt-type CVT at low vehicle speed range. At high vehicle speed range, the DCVT operates as a planetary gear type CVT, utilizes the belt-type CVT to change the gear ratio. The engineer who invented this mechanism must be a genius. The world's first CVT was the DAF 600 manufactured by the Dutch company DAF. This CVT used a rubber belt system, which was insufficient for transmitting high torque, and the engine of the DAF 600 had a displacement of 590 cc. The modern steel belt type CVT was first adopted in the 1970s by the Volvo 66. Subsequently, Japanese car manufacturers widely adopted CVTs. Fiat, Rover, and Audi also used them for a period, but they are no longer in use today. In 1999, Nissan adopted a half-toroidal CVT with metal discs, but this is also no longer in use today. The Toyota hybrid system uses a continuously variable system that changes its gear ratio by the load of the generator, but it is entirely different from a belt-type CVT. Now, the future of automobiles is divided into two paths, a world with only BEVs, battery electric vehicles, and a world where BEVs and hybrid vehicles coexist. It is likely that pure internal combustion engine cars will find it difficult to survive. In a world with only BEVs, transmissions are not needed. In hybrid vehicles, Toyota and Renault have their own transmission mechanisms, while Nissan and Honda have hybrid systems that do not require transmissions. Mercedes, BMW, Stellantis, and Mazda incorporate motors into their step-type AT. Regarding CVTs, it's hard to say that they have a bright future ahead. Thank you for watching. If you enjoyed this video, please consider subscribing to our channel. We'll see you in the next video.